Today we are going to discuss physical properties of alcohol, phenol and ethers. So let's read from the book. Alcohol and phenols consist of two parts, an alkyl or aryl groups and a hydroxyl group. The properties of alcohol and phenols are chiefly due to the hydroxyl groups. The nature of alkyl or aryl groups simply modify these properties. First property is the boiling points. The boiling points of alcohol and phenol increases with increase in the number of carbon atoms due to the increase in van der Waals forces. In alcohols, the boiling point decreases with increase in branching in carbon chain because of decrease in van der Waals forces with decrease in surface area. The OH group in alcohol and phenol is involved in intermolecular hydrogen bonding as shown below. So here you can see this is the intermolecular hydrogen bonding in alcohol, and here there is intermolecular hydrogen bonding shown in case of phenol. Now let's try to understand the meaning of these lines. So let's discuss the boiling point. Boiling point depends on two factors. First is the molecular mass. So here first is the molecular mass. Second is the intermolecular force of attraction. Intermolecular force of attraction. So boiling point is directly proportional to the molecular mass, and it is also directly proportional to the intermolecular force of attraction. That means heavy molecules have higher boiling points, or the molecules which have higher molecular mass will have high boiling point. Now come to the second factor, that is intermolecular force of attraction. Generally, every molecule has weak van der Waals force of attraction. But in addition to van der Waals force of attraction, if any molecule has dipole-dipole interaction or hydrogen bonding, it increases the boiling point of the molecule. So let's try to understand it. For example, there is methanol. Here CH3OH, and another is the ethanol, C2H5OH. So for example, if I ask you to compare the boiling point of methanol and ethanol, so the molecular mass of methanol, obviously it is less than the molecular mass of ethanol. That's why the boiling point of methanol will be less than that of ethanol. Now come to the next factor, which is intermolecular force of attraction. All the molecules have weak van der Waals force of attraction. Van der Waals force of attraction. In alcohol and phenol, there is OH group. Because of the presence of OH functional group, these molecules have hydrogen bonding. So in addition to van der Waals force of attraction, alcohol and phenols have hydrogen bonding. Due to presence of additional force of attraction, which is hydrogen bonding, alcohol and phenols have higher boiling point as compared to the alkanes. Now when you see, this is the alcohol, for example ROH, this is alcohol, and we already discussed the structure of alcohol. So in alcohol, this is alkyl group and this is oxygen. Oxygen is bonded to hydrogen. Oxygen has two lone pair of electrons. Due to presence of these two lone pair of electrons, the shape of alcohol is slightly bent shape. Now you can draw hydrogen bonding between different alcohol molecules. So here, this is another ROH. So as hydrogen is delta positive and oxygen is delta negative, there is hydrogen bond between electronegative oxygen and electropositive hydrogen. So that's how you can draw hydrogen bonding between two alcohol molecules. Now let's try to draw hydrogen bonding between two phenol molecules. So this is between two phenol molecules. So this is benzene ring it is bonded to oxygen and oxygen is bonded to another hydrogen. So similarly, you can draw another structure here. So this is benzene, another phenol molecule. It is bonded to oxygen and oxygen is bonded to hydrogen. In phenol also there is electronegative oxygen and electropositive hydrogen. So there is hydrogen bonding between electronegative oxygen and electropositive hydrogen. So that's how you can draw hydrogen bonding between two phenol molecules. So in addition to van der Waals force of attraction, there is hydrogen bonding. That's why alcohol and phenol have higher boiling point as compared to corresponding alkanes. Now come to the second point of branching. So how branching affect the boiling point of alcohols? So here if I take the example of 5-carbon pentanol. Let's draw different isomers of pentanol. So this is CH3, CH2, 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 CH2 and it is bonded to OH. So this is N-pentanol, unbranched isomer of pentanol. Now draw the another isomer CH3 single bond CH2 single bond CH CH2 OH and here it is bonded to another CH3. So it is one branched isomer. Now draw another structure in which there is one more branch. So CH2, it is C, it is bonded to OH. Here this is bonded to CH3. On this side it is bonded to another CH3. Now let's draw the 3D structure for first isomer. Each carbon is sp3 hybridized, means every carbon has tetrahedral geometry. Now let's try to draw 3D structure of N-pentanol. So here there are 5 carbon chain, 1, 2, 3, 4 and 5. This fifth carbon is bonded to oxygen and oxygen is bonded to hydrogen. As each carbon is sp3 hybridized, so here there is front bond, this is rear bond, this is front bond and this is rear bond. Here there is front bond and this is rear bond. Similarly, this is front and this is rear bond. And everywhere hydrogen is there. So here this is hydrogen, hydrogen. And here also it is CH3. Now similarly draw the 3D structure for second isomer. There are 4 carbon long chain. So 1, 2, 3, 4. This fourth carbon is bonded to oxygen. Oxygen is bonded to hydrogen. And there is a branch of methyl at second position. So here the second carbon I may draw methyl with front bond. So here this is carbon CH3 and here this is hydrogen. So similarly I can draw this structure for front and rear bonds. Now draw the 3D structure for third isomer. So there is chain of 3 carbon, 1, 2, 3. This third carbon is bonded to oxygen and oxygen is bonded to hydrogen. At this first position there are 2 methyl group. So there is one methyl group bonded to rear carbon and one is bonded to front carbon. So here this is CH3 and this is CH3. CH3 means it is also tetrahedral geometry. And here there is front bond and it is rear bond. So when you try to pack such molecules, so if you try to pack 2 molecules of N-pentanol, when you try to pack them, so there will be certain points at which they may in contact with each other. When you try to pack 2 molecules of second isomer, the branch of methyl may create hindrance for the close packing of 2 such molecules. When you try to pack 2 molecules of third isomer, there is a branch of 2 methyl groups. So because of these 2 methyl groups, the close packing of third isomer will be more difficult. Close packing in the sense, the point at which 2 molecules come in contact. When two molecules come in contact with each other, the van der Waals force of attraction comes in action. When there is no contact, there will be no van der Waals force of attraction. So that's why, here I can write van der Waals force of attraction is directly proportional to the point of contacts. When there is more points of contact, there will be more van der Waals force of attraction. So here the force of attraction is directly proportional to the point of contacts. In case of first isomer, there is more point of contact. So there will be more force of attraction. And in case of second isomer, there will be less point of contact as compared to first isomer. So there will be less van der Waals force of attraction. While in case of third isomer, due to presence of more branches, there will be less points of contact. So that's why in case of third isomer, van der Waals force of attraction will be least, while it will be more in case of first isomer. So when there is more van der Waals force of attraction, van der Waals force of attraction is directly proportional to the boiling point. So that's why when you compare the boiling point of these isomers, so first isomer will have maximum boiling point and third isomer will have least boiling point. Now let's read from the book. It is interesting to note that boiling points of alcohol and phenols are higher in comparison to other classes of compound, namely hydrocarbons, ether, haloalkanes, haloarenes of comparable molecular mass. For example, ethanol and propane have comparable molecular masses, but their boiling point differ widely. The boiling point of methoxymethane is intermediate of two boiling points. Here comparison of boiling point is given between ethanol, propane and methoxymethane. They all have comparable molecular masses. The molecular mass of ethanol is given 46. For methoxymethane it is also 46 and for propane the molecular mass is 40. So they all have comparable molecular masses. But in case of methanol the boiling point is given 351 Kelvin. For propane, it is 231 Kelvin and the boiling point of methoxymethane is between ethanol and propane and it is 248 Kelvin. In case of methanol, due to presence of OH, there is hydrogen bonding. So because of the hydrogen bonding, the boiling point of ethanol is maximum among them. In case of propane, there is no OH. There is no electronegative oxygen. So that's why there is just van der Waals force of attraction present between the molecules of propane. While in case of methoxymethane, due to presence of oxygen, which is electronegative element, there will be dipole-dipole interaction. So the intermolecular force of attraction will be stronger as compared to non-polar propane. So there is intermediate force of attraction between the two molecules of methoxymethane. That's why the boiling point is also intermediate. The high boiling point of alcohol are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in ether and hydrocarbon. Now come to solubility. Solubility of alcohol and phenols in water is due to their ability to form hydrogen bond with water molecules, as shown. The solubility decreases with increase in size of alkyl or aryl group. Several of the lower molecular mass alcohols are miscible with water in all proportions. Now let's try to understand the solubility in water. For any molecule to be soluble in water, first thing which is required is that the molecule should be polar. So polar molecules are soluble in water, and second property which is required for the solubility in water is the ability to make hydrogen bond with water molecule. Hydrogen bond with water molecule. And in alcohol and phenol, they both are polar molecules. So when you see this is phenol oxygen and it is bonded to hydrogen. So when you see the phenol molecule, so oxygen is electronegative and hydrogen is electropositive. Due to difference in electronegativity of oxygen and hydrogen, the molecule is polar. So this molecule is polar. Being polar, it is soluble in water and it can also make hydrogen bond with a water molecule. So if I draw the structure of water molecule, so let's draw hydrogen bonding with a water molecule and phenol. So here this is water molecule, oxygen, hydrogen and this is hydrogen. So here you can draw hydrogen bonding between phenol and water molecule. So there is hydrogen bonding between phenol and water molecule. So phenol can make hydrogen bond with water and it is polar also. That's why phenol is soluble in water. Now let's check the solubility of alcohol in water. So this is CH3OH. This is methanol. And here also there is electronegativity difference between hydrogen and oxygen. So this is electronegative and it is electropositive. Now you can draw hydrogen bond between methanol and water molecule. So this is water molecule. So here you can draw hydrogen bond between electropositive hydrogen of methanol with electronegative oxygen of water. But there is one point is given, the solubility decreases with increase in size of alkyl or aryl group of hydrophobic groups. Now when you increase the size of alkyl group, if I increase the size of alkyl group, for example this is butanol. So this is CH3, it is bonded to CH2, this is CH2, CH2 and this is oxygen, it is bonded to hydrogen. So the polar part of molecule is the OH part. This is the polar part of the molecule. But when you see the hydrocarbon chain, there is no electronegativity difference between hydrogen and carbon. That's why this part of the molecule is non-polar. This part is non-polar part of the molecule. As this part is non-polar part of the molecule, this will be less soluble in water, or you can say this will be insoluble in water. This part, because of this part, the molecule will be insoluble in water because only polar molecules are soluble in water. That's why it is written here, lower molecular mass alcohols are miscible with water in all proportion. But when you increase the hydrophobic part of the molecule, that will be less soluble in the water. Now let's try to solve these examples. Arrange the following set of compounds in order of their increasing boiling point. First one is given pentane 1-ol, butane 1-ol, butane 2-ol, ethanol, propane 1-ol and methanol. Now let's try to solve this question. And you know, boiling point is directly proportional to the molecular mass. So molecule having higher molecular mass will have higher boiling point. And here we have to arrange these molecules in increasing order of their boiling points. So first of all, identify the molecule with have least molecular mass. So here there is methanol. So here we can write methanol. It will have least molecular mass. So it will have least boiling point as well. After methanol, there is ethanol. So here we can write ethanol. After ethanol, we can write propane 1-ol. So here this is propane 1-ol. After propane 1-ol, we have to compare between butane 1-ol and butane 2-ol. So we just have to decide between butane 1-ol and butane 2-ol which will have higher boiling point. Pentane 1-ol will obviously have highest boiling point. The maximum boiling point will have pentane 1-ol. But here we have to decide between butane 1-ol and butane 2-ol. So let's draw the structure of butane 1-ol. This is CH3, CH2, 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 OH. This is butane 1-ol. Now draw the structure for butane 2-ol. So this is CH2, CH, this is CH3, and at second position there is OH functional group. Butane 2-ol. So when you compare the structure of butane 1-ol and butane 2-ol, here there is OH group which is present at second position. So you can consider it as a branch of the molecule. On increasing the branching, the boiling point decreases. So here we can see butane 1-ol will have higher boiling point than butane 2-ol. So here this is butane 2. This is the increasing order of the molecules according to their boiling point. Now come to the second question. Pentane 1-ol, N-butane, pentanol and ethoxyethane. Now let's draw the structure of these molecules. So first is the pentane 1-ol. Pentane 1-ol is CH3, CH2, 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 OH. Means there is OH functional group. N-butane means this is hydrocarbon. CH3, CH2, CH2, CH3. This is N-butane. Now draw the structure of pentanol. Pentanol means it is aldehyde functional group. CH3, CH2, 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 C double bond O H. This is pentanol. Now draw the structure of ethoxyethane. This is an ether. So it is CH3, CH2, O, ether functional group. On the other side also CH2, CH3. So due to presence of OH functional group, this molecule is polar and it has hydrogen bonding as well. And butanes are non-polar molecules. So they are non-polar molecule. So there will be only van der Waals force of attraction working between two molecules of butane. Now come to pentanol. In pentanol there is carbonyl functional group. Due to presence of carbonyl functional group, this molecule is polar molecule. But there will be no hydrogen bonding. So hydrogen bonding will be absent in case of pentanol. Now come to ethoxyethane, which is an ether. So these ether molecules are slightly polar. They are slightly polar molecule. They are not as polar as pentanol. And we have discussed earlier also, boiling point is directly proportional to the intermolecular force of attraction. Intermolecular force of attraction. Hydrogen bonding is a strong force of attraction. That's why pentanol will have highest boiling point, because there is strong hydrogen bonding is also present in the molecule. So when you try to arrange them in increasing order, butane will have lowest boiling point. Then after butane there will be ethoxyethane, and then there will be pentanol, and at fourth position you have to assign pentanol. It has highest boiling point. So here the answer is also given: N-butane, then ethoxyethane, then pentanol, and pentane 1-ol will have highest boiling point. In the next video we will discuss chemical reactions.